Hi, I'm Ben-Yaakov. The title of this presentation is Basics of PWM Converters Controller Design. This is the part 3 of a lecture entitled Peak Current Mode PCM. Now part 1 and part 2 include the background for this presentation. I highly recommend that you first watch these parts. Links are given in the comment section of this video. You can just click the links and get to the part 1 and part 2. Now, why do we wish to have current feedback in PWM converters? There are a number of reasons. The first obvious reason is the case in which we like to regulate the output current. That is, we like to have either constant current or maybe a current that is regulated. And for this, we need, of course, a current feedback. This is not the subject of this presentation. We are not dealing with this situation. What we are dealing with is a converter that needs to stabilize the output voltage. That is a voltage regulator. Now, the reason for using current feedback in a voltage regulator is to improve stability and the dynamics of this regulator. In this case, we are going to have dual loop control. That is, we are going to have two loops, one of a current feedback and one for a voltage feedback. And we'll see that the current feedback offers many advantages over the basic voltage mode controller. Another reason for using current feedback is a better short current protection. That is, a system with a peak current mode has a built-in protection, and we call it a cycle-by-cycle protection, so as to protect the transistor from overcurrent. And we'll see this in a while. Now, current feedback then is used in voltage controller to improve the dynamics and stability. Now, the system of a voltage mode control suffers from the fact that the transfer function is a second order. And as is shown in part 1 and part 2 of this lecture, a second order system is more difficult to control, and therefore by adding a current feedback, what is really happening is that the second order system becomes a first order system. The reason, or the basic reason for that, is that whenever you take a feedback from a state variable, and in this case it will be the inductor, whenever you get a feedback signal from the state variable, this will reduce the order of the system. That is, if we have a second order system and we have a current feedback from the inductor, then the system becomes a first order, and I'll show it in a while. So here we have the very concept of a current feedback. Here is a buck converter. This is the switcher, the diode, the inductor, output section, capacitor, and there's a filter capacitor plus a resistor that emulates the load. We take a sample of the current, and there is some conversion here which converts actually the current through a voltage. This will be like a resistor in between, and we compare the voltage here, which is a proportional to the current, to a set of reference signal here. This is the V sub E. Actually, it comes from an error amplifier. We'll see it later. But for the purpose of the present slide, this is like a constant voltage here. Okay? So we compare this current to this constant voltage, and any error here is amplified. Is fed to a modulator which produces a duty cycle. So this is a closed loop on the current, and what will really happen is that if the gain, the loop gain, that is the gain from here through the amplifier, through the modulator, is indeed very high, much larger than 1, then the error signal here, that is the difference between VE and this return, becomes very, very small. And therefore you might say that I out times N will be equal to VE, and therefore the current is actually controlled to be 1 over N times VE. So if I have a small signal here, like it's riding on the large signal, I'll generate a small signal here, which is proportional to this signal. So in this case, we are sort of losing the behavior of an inductor, and in fact, this inductor becomes like a current source, okay? And therefore, the current, the transfer function between this small signal, which I'm interested in here because of the dynamics depend on the small signal response, the ratio between the small signal of the current to the small signal of the error here is flat, it's constant. So this implies that in this particular closed loop for the current, we have here a constant current. That is, the constant current is a function of small signal of this error signal. So this current now is fed to an RC circuit, which is a first order circuit. So the transfer function between the error signal here, small signal error signal, and the small signal output voltage will be of this shape. That is a constant and then a breakpoint at 1 over 2 pi C out RL. This is the RC of the output section. So as a result, we have now a first order system, not a second order system like the original buck converter, but a first order system that is much easier to control or to close the loop or to design a phase compensator for. So here, how we are going to implement the full system. We have a inner loop. This is the current loop, the inner loop, measuring the current of the inductor, comparing it to the error signal, and then feeding it to the modulator. This error signal now is an output of an error amplifier which compares the output to the reference which is required. There might be a voltage divider here, but let's see that we are comparing the output to this reference. So what will happen is that whenever the output is different from V reference, we'll generate an error signal which will change the level here, and consequently the current will change so as to close the gap and get back the output voltage that is specified by this V reference. So this system here is an inner loop, and now the outer system, the outer loop, what this amplifier sees is actually a first order system. So this phase compensation here can be done on the assumption or can be based on a first order system, which is of course very easy to do as compared to a second order system, and this is again covered in part 1 and part 2 of this lecture. So here what happens? We had this second order system which is shown here in like a border plot with straight lines. This is a resonant peak of this buck converter, and then it goes down minus 40 dB per decade, and then there might be a zero, so it'll go 20 dB per decade. This portion then is the one that we usually will close the loop at, that is the crossover will be somewhere here, and since it is a minus 40 dB per decade, it will require like a double zero type of a controller. However, when we apply the current loop, the inner current loop, the system becomes this first order, this portion here. Again, when we lose the current loop, that is the bandwidth of the current loop would be maybe up to here, and then of course we go back to the minus 40 dB per decade. But this section here is very nice, and we can close the loop, say up to here, and get a very nice response. So let's see how we actually implement the peak current mode. To understand it, I like to go one step backward and look at the voltage mode PWM modulator. In this case, we have a power stage, we have a divider, error amplifier, and here's the modulator. This is a typical controller that we might have. Here's the error amplifier, the modulator, and a driver to drive the MOSFET here. So what is the modulator in the voltage mode PWM? What we have here is a comparator which compares the error signal coming from the error amplifier to a ramp type, a triangular repetitive wave, which is generated by an oscillator. So we compare this error signal to this wave, and at the cross here we change the output, or the output of the comparator is changed, and as a result we are getting this duty cycle response. That is, the higher or the lower will be VE, the T-on time will change linearly. So this is a PWM modulator. Now we can show that the D-on resulting from this modulator will be like VE is the error, V sub V is the valley, and then the difference here between the peak and the valley, this will be the value of the duty cycle. This is for voltage mode PWM. In the case of peak current mode modulator, the story is entirely different, okay? We don't have a regular modulator. In fact, the duty cycle is sort of generated in an entirely different way. Here we have a clock. This clock is generating pulses at a given frequency. This is the switching frequency. For each, say, leading edge of this clock, this flip-flop turns on and this Q goes high, and the driver will turn on the transistor. So at the beginning of each cycle, we are turning on the transistor. Of course, when we are turning on the transistor, and I'm showing here a boost converter, the current will start rising. Then we have a comparator, which on one side we're going to have V sub E. This is coming from the error amplifier. I'll show it in a while. Let's assume it is constant now. And this here is a voltage which is proportional to the current of the inductor. That is, there is a sensor here and translating the current into this voltage. We are comparing two voltages. Once this voltage reaches the value of V sub E here, the comparator will change the state at the output, and it'll reset this flip-flop, turning off the transistor. So the current starts to rise at the beginning of the pulse and stops when the current reaches, or the voltage equivalent to the current reaches V sub E. This duration here is the D on, the T on of the transistor. So this is entirely different. So here is how it's actually implemented. We have the transistor, we have an inductor. Now in this particular case, which is very common and very popular, we're not measuring the current in the inductor, but rather relying on the fact that when the transistor is on, the current through this series resistor is equal to the current of the inductor because the transistor is short. So we are measuring this inductor current by the voltage drop across R sub S. There is a filter here because as this transistor is turned on by the gate pulse, this leading edge transition through the capacitance between gate and source will inject a spike here. And this spike, if uncontrolled, will affect this comparator and not the ramp of the current. So here we have a simple RC circuit to sort of attenuate these spikes. I'll show you in a minute that there is a more sophisticated way to get rid of this spike, but let's assume that we have this filter here. So as the transistor is turned on, because the clock producing a pulses, turning on the flip-flop, turning on the driver, turning on the transistor, and the current starts to rise. As the current starts to rise, it eventually reaches this V sub E point. The output of the comparator will change, and the flip-flop will change state to the off polarity, and therefore the transistor will be turned off. Now this error signal here is the output of this error amplifier, which is sampling or looking at the output or part of the output and comparing it to V reference. I'm not showing here the phase compensation which has to be put in, because the system from here, VE, to the output is, as I've said, a first order system, but nonetheless, you do need phase compensation in order to get the bandwidth that you wish, and of course stability, the phase margin that you specify. Okay, now here what happens, suppose the voltage will change from the reference value, say it's going up. If it's going up, this VE will change. As this will change, then the reference to the current will change, and the current will be higher or lower as required with this negative feedback, so as to restore the value of the output. So the outer loop is responsible for the stabilization or regulation of the output voltage, while the inner loop is actually responsible for the current feedback, which is also generating the duty cycle and also reducing the order of the system. So this is how a current mode is actually operating. Here are some waveforms that are, I think, of interest. This is the clock. This is the ramp of the clock, which we haven't seen yet, and it turns out it has some importance. I'll talk about it in a little while. So this is actually controlling the basic switching frequency. So whenever the clock starts, we have the transistor turned on, and here is the spike I was talking about. And then we see the voltage, which is proportional to the inductor current, getting high. In many controllers, and this is actually part of a data sheet of a current mode controller, we have a special circuit that will blank the leading edge of this pulse. That is, this part will not reach the comparator, it'll be blanked out. So what reaches the comparator is this part here. So although this spike could be high and trigger the comparator, it is not seen by the comparator because it's blanked out, and we only see this part here. And here, this is the place where the current or the voltage proportional to the current is reaching this V sub E, and then the transistor is turned off. We have some problems with peak current mode. One of the major problems is what's called subharmonic oscillations. Subharmonic oscillation means that we have instability, and the system starts to oscillate at frequencies which are subharmonics of the switching frequency. That is, the oscillation will be at frequencies like half the switching frequency, quarter of a switching frequency. This is very annoying, and of course makes the system useless, because you cannot tolerate a system which oscillates, and the voltage at the output will not be stable. However, this phenomenon start to appear only when the duty cycle is above 0.5. When the duty cycle is below 0.5, there are no subharmonic oscillations, and I'll explain it in a few minutes. So if the system is designed such that the duty cycle will always be confined between 0 and 0.5, that's fine. There will be no subharmonic oscillation. However, if the system will go into a duty cycle which is higher than 0.5, you need to do something in order to eliminate, or in order to arrest these oscillations. And what you have to do is to add a slope compensation. And I'll talk about it in a couple of. Let me first of all explain what is the nature of this subharmonic oscillation and how they actually get started. There are many explanations, or many ways to explain this phenomenon. I'll use here the geometric explanation, which was first offered by Professor Middlebrook, or the late Professor Middlebrook, and which is rather easy to understand. So here is the inductor current, or actually the voltage proportional to the inductor current. Here is V sub E. And of course, as the current goes up, it'll hit this point. This is where the transistor turns off, and therefore we'll start seeing here a decrease in the current, because now we are in the off state of the converter. Suppose now that there is some interference or a change in the inductor current due to, say, loading, okay? And therefore, at this particular time, rather than having this current, we are going to have a little bit higher current. As a result, we are going to hit this V sub E at this point, and then it'll go down, the current, by this slope here. So we started with some delta I here, and one can show by some geometrical calculation, which I'm not giving here, one can show if you start with a delta I sub 1 and end with a delta I sub 2, then this delta I at the end will be smaller than this one. This means that the next cycle, delta I sub 3, will be even smaller, so this disturbance will die out. However, as it turns out, if the duty cycle formed by the current hitting this V sub E is larger than 0.5, that's the 0.5 point, and you start with the delta I sub 1, you'll add up with delta I sub 2, which is larger than this delta I. So therefore, the delta I sub 3 will be even larger, and hence we are going to have oscillation. So in this case, if the duty cycle is larger than 0.5, the system will be unstable, and we are going to have this subharmonic oscillation. So what can we do in order to arrest these oscillations and stabilize the system? Well, what you have to do is to change this reference level by adding a slope to it. This is called the slope compensation. That is, rather than having this V sub E constant, you add to it a ramp, downgoing ramp, like this. And again, one can show by some geometrical simple calculation that in this case, for duty cycle smaller than 1, if you start with some delta I, you will end up with a smaller delta I. And even if the duty cycle is larger than, this is the 0.5, larger than 0.5, you'll start with a delta I, and you'll add with a delta I, which is smaller. So this system is stable, and no subharmonic oscillation will be generated if you add this slope compensation to the V sub E. Now, the amount of slope compensation that you need is equal to the sum of the absolute values of the inductor upslope and downslope. This is not the inductor, but rather the voltage, which is linear or proportional to this inductor. That is, the slope that you need here has to be equal or larger or steeper than this slope here plus the absolute value of this slope here. This is the rule that actually was found by our professor. So how can we add this slope? Well, suppose we have somewhere in the system this ramp. We can add it here by sort of a summation between the output of the error amplifier and this slope, or we can actually add it here, but this should be in an opposite direction, because what is really important is the difference. So if for the V sub E I have to add the downgoing slope, then for the current I have to add a upgoing slope. So from where do I get these slopes to add to these points? Well, we have the oscillator. This is the oscillator of the peak current mode controller. Oscillators are usually built by having a capacitor which is charged by a current source. Once the voltage of this capacitor reaches a certain value, then this resistor is discharging it back. So here it is. We have the ramp going up, and then it discharges. The ramp going up and discharging. This is the oscillator. Now, we have this portion here, which is the ramp. So we can use this to add it to V sub E or to the current sensing resistor, so as to compensate the level and get the slope compensation that we need. Aside from the fact that the system is now first order for the outer loop, there is another benefit which is very important, and that is a overcurrent protection. The reason that we have this sort of built in is that as the current of the inductor goes up and the voltage goes up here. When it will reach this point, it will be turned off. That is, the transistor will be turned off automatically because the flip-flop is turned off and then there is no input to the driver. So by clamping this voltage to a certain level, you are sure that the transistor current will never be higher than this level. I mean, after the translation to the voltage. So this is, as we call it, a cycle-by-cycle protection, which is, of course, very nice. The peak current then of the inductor will not be higher than the V clamp, that is the voltage here, times Rs, which is the translation of the current into voltage. So let me summarize what are the advantages and disadvantages of the peak current mode. We have a cycle-by-cycle protection. We have a better dynamics because the system is actually, due to the inner loop, becoming a first-order system. And then we have a problem of a leading-edge spike, which we have to filter out or blank it out, as I've shown. And then we have the problem of subharmonic oscillation, which, of course, if we keep the duty cycle below 0.5 is no problem, and above that we do have to add this slope compensation. Let me at the end add a few words about average current as opposed to peak current mode. Average current mode is also a current feedback. Here we measure the current, but unlike the previous case, we go through an amplifier which attenuates the high frequency. So here we are going to have only the low frequency component here, or the DC component of the inductor current. So we don't see here anymore these ripple, or they'll be highly attenuated, so we practically see here like a DC current. Now again, we have an outer loop which compares the output to the reference, and of course there is a phase compensation. Again, in this case, from here to the output, it's a first order system because of the inner loop. However, we don't have a cycle by cycle protection, and the dynamics will be a little bit slower because we don't see very quick changes in the current. So we get here also the benefit of the first order as before, rather than having on the original stage a minus 40 dB per decade, but it lacks some of the features of the peak current mode. This brings me to the end of this presentation. I thank you very much for your attention. I hope you have found this presentation of interest and that it will be useful to you in the future. Thank you.